Hey guys, how you doing? There we are.
Okay, there should
You
be
have me
people
now?
in. Can you let everyone in that's waiting?
Can I let in Walid? Because there I am. I just want to get him ready and then I'll let everyone in. Is that okay? Thanks. Hi, Walid. Hi, Walid. How are you?
Everything's me?
There you are. Sorry, I'm very sorry.
No worries. I
yeah.
just make sure that I'm connected correctly. No problem from my side.
Yeah, no, that's my fault. No, I was late, so yeah.
Okay. Just before we go, how we can share the screen?
Yeah, you should be able to share it. I've made you host now.
Yeah. Okay.
And once you're ready, I can let everyone in.
Okay.
So sorry about this.
No worries. Just let me know when it's ready. Do you see it at the moment?
Yes.
Okay. Should I put it on that sort of mode, is complete mode right now? Just one sec. Do you see it?
Yes.
Okay. Perfect. Then yeah, that'd be very good. I just will move my site to this screen.
Yeah.
That. So now everything is clear.
All right, you might need to let everyone in now that because we can't have co-hosts apparently. This is DSA asked me to set it up myself, and I have, but we'll have to fine tune it. Sorry. When you're ready, if you're happy to let everyone in, and then I'll introduce. So sorry. Thanks, Leah.
No worries. No worries.
Too.
Should I do that myself? You said.
Yeah, you'll have to. So if you go to your participant screen, you should be able to let people in.
Where's our participant screen? There's 19 people there.
Yeah.
Should I do invite or what? I haven't done it.
If you click on it, and then you should be able to see everyone that's waiting to come in. Can you see that?
I just yeah, definitely. I can admit everyone. Okay, perfect.
Yeah. Thanks, Walid.
No worries.
All right. Hi, everyone. Sorry for starting late. That is my fault because I put together this meeting and they had to wait for me to let you all in. So apologies. I had Leah messaging and reminding me. So not a very good start to today's webinar, but we're back on track. And thank you for your patience. We're very excited to present to you our November ARGA webinar. And just wanted to quickly acknowledge that we are coming to you across Australia and beyond, and that we're meeting virtually, but I'm here in Ghana country and like to acknowledge our elders past, present and emerging. So I don't want to muck around too much, but we probably have some announcements. We do have some other webinars coming up. I should have them in front of me, but I don't. I don't know if Leah would like to quickly do a shout out to the next webinars before we get started with Walid today.
Yeah, thanks everyone. I hope that everyone is online at the moment. I haven't forgot anyone. Just to make sure that everyone is already in.
Yes.
Perfect. Okay, thanks everyone for giving me this opportunity to present today on the interface sampling and the indicator minerals for mineral exploration. Of course, the topic today is a group of case studies and some basic understanding of the regulus, and a number of companies has been involved in that sort of research in collaboration with CSIRO. For people who doesn't know me, I'm Walid Salama, Principal Research Scientist at CSIRO and the Team Leader of Mineral and Water here at the Mineral Resources Business Unit in CSIRO in Paris. Yeah. So a bit of background about the topic today. As you know, Australia is or large area of Australia are covered by transported cover. And especially in the area of transported cover, surface geochemical exploration sampling media have a limited application, especially of the transported cover is deep. So if we have sort of success of sampling near surface and finding anomalies when the cover is almost up to 20 meter, or could be up to 30 meter maximum. After that, the application of this surface geochemical technique like soils, termite calcrete, or even termite samples have a limited application. So we wanted to use different techniques here. The topic of this presentation is about interface sampling, and recently started to focus mainly on the indicator minerals in the area of transported cover. Of course, the idea of interface sampling, that metal can disperse through the cover, either in a chemical, like mechanical dispersion, or physical weathering and erosion, or through the chemical mobility of the metals through the cover. Here you can see that, of course, to show the main problem there, that the surface of many parts of Australia is like this, especially in the Granite Craton, looks like this. Let me put the laser pointer. So the surface of Australia looks like that, flat land, almost covered by soil and vegetation, lags on the surface. And the Australian continent have almost more than 75% of the land surface is covered by regolith. And the geological map of Australia looks like, as you have almost of this percentage covered by sedimentary basin of Paleozoic age, and the areas of cratons and the origins of Proterozoic and Archean age, mainly in different parts of Australia. Even this area is also covered by different thicknesses of transported cover. Range in many cases from few to 100 meters in this area of sedimentary basin, and of course secure the prospective area for mineral exploration. Before we go, as I mentioned to you, the area of transported cover is the focus of today. But before we go there, to just to know exactly where you in the landscape, the landscape has been classified based on the red scheme or the area of residual enrichment and complete weathering profile like this, and areas of erosional regime where part of the residual weathering profile is eroded, and the area of depositional regime where most of this erosion of the landscape has been deposited somewhere in the landscape to form different sedimentary sequences, ranging from paleochannel sediments, ranging from lacustrine sediments, and also colluvial-alluvial, aeolian sand, salt lakes. All of this is part of the transported cover. That's when we go in the Granite Craton or shallow cover area. Of course, this type of cover is going to be changed to different types of cover, like a Cretaceous, or even Eocene when you go for the marine basins, like Euclid Basin, for example. This is a landscape to show you the exact location of this type of landscape, complete weathering profile. When you remove part of it, exposing the saprolite underneath, this is truncated regime. When you root all of that material and deposit in between, that's a depositional terrain. So this is very important to understand. As I mentioned to you, the area of transported cover when it's less or up to 20 meters is area of shallow cover. When it's above that, we consider this is the area of depositional or deep cover. Before we go, if you go back again here to see the difference between that sort of areas like this residual terrain and this area looks like in a similar way. This area called, or the top of the weathering profile called the lithic residuum, where the material inherited from the mass wasting and concentration of the metal during weathering. This is the area that could be also duricrust on the surface, but it can be inverted landscape where that's what's happening. You may have residual area and erode this material deposited in the low-lying areas and re-cement it, and later on erode the surrounding areas to form different landscape. This type of material here we call ferruginous, which is in the top part of the landscape. But this is considered as transported or transported cover as well. It's not related to the underlying rock, so it can cause problems when the metals is enriched in it, especially in Africa and South America. Plenty of these false anomalies happening in this area, which was considered as residual, now is considered as transported. Example of this material when we consider the interface sampling, because some of these materials I mentioned here, this type of the ferruginous, sometimes it could have some multi-element anomalies here. This is example from Yamana terrain. When we see, for example, ferruginous gravels not related to the underlying rocks, This is considered as an unconformity in between. Even you can see it in the exposure. Looks sort of fragmented on the top of residual material. But when we do, and as I mentioned to you here, multi-element anomaly could be also promising for explorer to drill underneath. But when you do look for the chemistry of this type of material, you can see, for example, titanium over zirconium ratio, showing variation between this material and the underlying rock. This is a mafic rocks. This is weathered to saprolite of different composition, mainly ferruginous saprolite, and topped by these ferruginous gravels, cemented, as you can see, and topped by aeolian sand. When you apply some ratio for titanium over zirconium ratio, you can see that mafic rocks and the overlaying weathering profile normally above 60. When you move to this material, you go down to almost less than 4, and that's indicative of more felsic source rocks. So this material can be derived from different source rock, not related to the underlying rocks. You can see also, for example, uranium anomalies here. Also, normally it is not changing from the fresh rock to the weathering profile, and when you go there, it changes. So some of these boundaries here is very important to understand and to determine based on some of the geochemical variation using some selected some selected elemental ratios. It's very important to understand that. Okay, because as I mentioned to you, plenty of stuff in Africa along slope, you find this material, and when you drill through it, you don't consider the paleo landscape and how you can go up slope to follow up the main source of this material. And this is example from Mali, for example, when you see the landscape have a latritic residuum, how complex the landscape there, and you must be like taking care when you're sampling stuff and understanding the nature of the surface material. Latritic residuum here is eroded, and the material from the latritic residuum coming in the eroded part, feeling this is as a ferruginous gravels. With time, this ferruginous gravel is cemented, as you see it here, forming ferricrete, and this is lateritic residuum. So this is not related to underlying rock. This is related to this. Later on, the ferricrete can be also eroded down and making another drainage system. And this area now is becoming on higher elevation. So you have a ferricrete and have a lateritic residuum here in between. All of this is not related to each other. So under this material, there's a big unconformity here. One of the interfaces that we're going to talk about in the next few slides. Before we go to that, as I mentioned to you before, the most important thing from that sort of landscape, the depositional environment. If you look for the depositional environment in the Yale Garnet Craton, we have a plenty of transported cover sequences has been deposited over either weathered bedrock or even fresh rock. The saprolite here, for example, is overlain by the oldest cover sequence is a Permian cover, and this is overlain by tertiary cover, and this is overlain by quaternary sediment. That's a very simple way of looking for this type of transported cover. Sometimes, in many cases, we found this is a sketch, but most of the Permian cover is sitting actually in an area of fresh basement rocks. I'm going to show you one of the examples from this Permian cover. But the idea from this one that the formation of the saprolite having in a wetter climate, and you can see this type of vertical lines here, which is all the 260 million years based on paleomagnetic mapping. And when we put the next type of weathering event, this dashed line, the blue dashed line, and then the last one in the red dashed line, you can see various climatic change which affecting the sedimentary cover. Almost all of this transported cover has been affected by chemical weathering and mechanical weathering. The top of the Permian, the bottom of the Permian cover is fresh. The upper part of the Permian cover is weathered. Most of the, or all of the tertiary cover is weathered, and the topmost part of the colluvial-alluvial is actually the weathering product of the residual ferruginous duricrust. And also lacustrine clays and aeolian sand is also belonging to this type of the cover. So this is giving indication that the cover itself is more complicated and more weathered, and the metal is expected to move from the saprolite through this type of the cover. We're going to show some of this, and we're going to go through this type of the cover, looking for the indicator minerals and also for the interface sample. Just to show that.
Sorry
Yes.
to interrupt. You might need to let a couple of people in if you don't mind checking the participants.
Yeah, sure. That's okay, perfect.
Yeah.
1 sec.
Sorry.
I'll look. Okay, no worries.
Thanks.
No worries. Okay, no worries. Done. Okay, so that's a vertical section to show you what's happening from the residual weathering profile on a fresh rock. And this is a Permian-Carboniferous glacial sequence. This is a tertiary inset valley sequence, and this is a quaternary aeolian sand and all other stuff of sedimentary cover coming in the quaternary. Oh, this is the summary of the process, and this is a summary of the product. As you see, the process is ending up of formation of clays and iron oxide in all of them, except when you go to the more arid condition in the quaternary system, you do more silicification and calcification and gypsification that associated with the arid climate, and also the formation of hardban and calcrete and silcrete and ferrite. All this is transferring from more humid climate to more arid climates. Of course, saprolite and ferruginization can happen during the arid climate on a different sedimentary sequences. Okay. Yes. So the idea of interface sampling here is actually very important to look for this slide. The interface sampling is two different types of interfaces. The interface, actually, the first one is a physical interface, which is actually sampling very close to the unconformity. The idea is depending that if you have any mineralization or either in fresh rock or in weather drop and overlain by transported cover, the mechanical weathering of this residual profile or even the fresh rock will move some of the material from this weathered material, which could include remnant of lateritic residuum or mineral grain or gossans that could be good for indication of the mineralization. And in the same times, it give a wide dispersion halo bigger than this size of the mineralization. So you can track it from distal footprint toward the mineralization. So that's very important to understand. This is the most important or one of the two different types of interface: mechanical weathering along with this physical interface, which is unconformity. So when you're going to sample through this type of the unconformity, actually depending on the nature of the unconformity. If you have an unconformity like a sharp, you can spot up the boundary between the transported cover and the underlying residual or weathered fresh rock. You can get, and especially if you drill through the transported cover in using RC ships or AC ships, you can get the lowermost meter and the uppermost meter and analyze separately. But if this boundary is a gradual boundary, for example, then you are not able to spot this. So you can come to the closest area that you think, and you can mix a few meters above and below, maybe 1 or 2 meters above, 1 and 2 meters below, something around that, and mix them together. If you are not sure about the boundary, then you can get the mixture of this type of the unconformity, and you analyze them. So this is the way we sample the unconformity. Here an example, for example, to show you what's happening, for example, with one of the gold deposits. This is a basement gold distribution in the area, and this is the main mineralization. And this is the extent of the mineralization. And here's the interface gold sampling. So when you sample this, you can even get a little bit slightly away from the dimension of the mineralization. When you look for also for the arsenic, for example, arsenic is a little bit tight, but it can be also show wide dispersion when you go with the interface sampling. And also why the interface sampling is very important. If you look, for example, from the recent big deposit happening undercover, especially in the Patterson and Pilbara, something like a hemi-gold deposit or even Haverian deposits and Winu copper gold deposits. This is overlain by very thick cover of Permian and Aeolian sand, and most likely this mineralization with a good grade coming in contact with the base of the transported cover. So sampling along this surface can bring a very good vectoring to the mineralization, especially if the mineralization is a little bit narrow, but some of these deposits are actually big deposits. You can get a little bit more evidence of this type of deposits. It looks like it could be a very good promising sampling media in this way when you sample close to the unconformity. Okay, so this is example of these 3 areas. Of course, many other deposits in the same area have the same signature. It looks for me like this is a good example, or many examples have the potential of using the interface sampling to find some of these deposits. Of course, this is in addition, if we didn't know exactly because we haven't done any work in this area. about if there's any hydromorphic dispersion through cover in any part of the cover, in the lower part or the middle part, or it could be going up through this type of the cover. And also, we don't know exactly how the surface of this how the unconformity, the topography of the unconformity looks like. It might be in some area come closer to the surface, so you can get some sort of evidence along higher within this type of the Permian and the aeolian cover. The idea also of this of the interface sampling is not mainly about mechanical erosion along the unconformity, but also we look for the chemical dispersion through cover. We were looking for the redox fronts or some of the enrichment within the cover. But the idea of the cover, depending that the fresh rock is weathered to residual regulus, and this residual regulus can concentrate some of the metals in it. And when you put the first unit of transported cover, there's some sort of reaction happening through different mechanisms. And this can be seen in detail in an 2016 Geology review. Different mechanisms working below the water table and others above the water table. Of course, this can transfer metal to the next unit, but the concentration of the metal is going to be even less than the residual material. And when you deposit the next unit and the next unit, the interaction going to happen and the metal going to move. And once you go move up and up, there is some sort of dilution happening of the concentration of the metals as you're going up through the sedimentary cover. So you can ending up with looking for pure BBB concentration near surface versus background, not a ppm level. And this is some of the example of the mechanism that we are looking for. Of course, these are some details. I'm not going to go towards that. You can read that sort of paper that I mentioned, but groundwater is the main driving mechanism that move the metals somewhere to the cover, and could be through biotic process or gases process or electrochemical transport to the cover. And very close to the surface, the termites can work, and also vegetation and some sort of other mechanism, like a capillary mechanism, can move the metals very close to the surface. So you can even transfer the metals to two process to the phreatic zone below the water table, and the other one can be taken up by the near surface sampling, meaning like vegetation and termite mounds. And when the water table is high, the metal can go close to the surface, but when you change it to more arid climate, the water table go down. And when it go high, metals can move, and if there's iron and manganese concentration, can take in a lot of metals in it within the cover, and this can be a number of these redox fronts, where the iron and manganese can suck a lot of metals, leaving them within the cover, and then the roots can reach this type of levels, and getting this metal higher and higher to transfer them to the surface. As I mentioned, we're looking for the physical interface, which is actually, as I mentioned before, mechanical dispersion of residual material across the boundary between the cover and underlying weathering profile, or even between the sedimentary cover sequences itself. Chemical mobility means that we are targeting these redox value fronts within the cover, which is based about the dispersion of the metals through by groundwater, the hydromorphic dispersion by groundwater percolating through the area of transported cover. This example show you how this type of the interfaces and why we have used those ones. This is a summary of some of the case studies and some of the locations that we are looking for. First of all, it is not easy to determine that sort of interfaces in some cases. For example, if you're going to look for this type of unconformity between the paleo channel clays and underlying saprolite. This is an example of transported clay from the paleo channel, and this one from the saprolite. Of course, you can see some color here, but this is from the core samples. If you see the rock shapes or from AC or RC, it might be difficult to see something like that. But this type of clay is more buggy, swelling clays due to presence of smectite. This is more clay. On the ground, you can discriminate. This looks like a ball. It looks like a ball stand high on the ground on a pile of the drilling. This is very soft. That's from the physical observation. But also, there's also other type of method you can differentiate between both of them. Some of the boundary of the mechanical boundary is very sharp, especially when the Permian cover sitting on a fresh rock. You can see, for example, Permian diamectite here sitting on a fresh rock, no weathering of the underlying rock in this situation. So this is very clear, and you can see it here. But when you go to the ship trace, you can see also some difficulties. So that sort of boundary is very easy You can see it very easy in diamond, but in chip trays, you need to be smarter to identify this type of interfaces. In terms of the mechanical dispersion, sorry, the hydromorphic dispersion and formation of this paleoredox front, you can see within the cover some area of residual enrichment of iron and manganese oxides inserted in the horizon. Above it and below it, the sedimentary cover is almost normal, something like this. But this area where we look for enrichment of iron and manganese, this is a redox front or chemical interface. Of course, also some of these metals in the surface, when it's rich in the surface, also enriched in iron and manganese, also another chemical interface. In some of the examples where we see why we sample across the unconformity between the Permian cover and the underlying fresh rock, because some of the gold can be enriched in the lower part together with some of the sulfur, for example. And I'm going to show you an example of this. When you sample across this, picking up the base of the transported cover or even the top of the fresh rock, you can still pick up the area of the mineralization by sampling that sort of interface. Zinc and gold, that's an example from this area, for example. But not only that, if you went to this area where we see this type of the chemical dispersion, you can see gold, for example, from the saprolite and underlying basalt hosting the gold mineralization. And this is the Permian cover here. The gold can move across this Permian cover there and reaching up to the surface up to 100 ppb gold. This is almost here 25 meters of transported cover. The evidence of reaction between the groundwater and the cover is shown here. The basal part is gravelly sand and gravel at the base. And once you go up to this molten zone, there's plenty of iron enrichment, reaction with groundwater, a lot of cavities, some brecciation with this material indicative of reaction with groundwater and metal mobility up to the surface. Of course, we are also looking for the indicator minerals, and we prefer to use the indicator minerals actually when the cover is almost fresh, sitting on a fresh rock, because we believe that under these circumstances, there's no chemical dispersion going to happen in this situation because the cover is fresh and the underlying rock is fresh and cemented by calcareous and sulfide cement. Mean that there's no chemical dispersion going to happen there. And we tested that by looking for enrichment within this material. It doesn't relate over the minute, it's just go and disperse it everywhere, not giving any clue. So in this case, we prefer to go and sample the base of the cover for chemical analysis and also for heavy mineral in the analysis. And you can see some of the sulfide still fresh, some of them complex and base metals and gold in different style. We're going to show you one example of this type of the cover. In other material, you can see other heavy minerals, some of them even gold and silver halides along that sort of unconformity coming from some of the gossan fragments along this boundary. This is another example of, this is from the gossan VMS system showing you the unconformity. This is a boundary between the tertiary paleo channel and underlying saprolite, and this is a quaternary sediment. Actually, the mineralization at the edge of this image. And when we sampling along this unconformity for some distance here, a lot of ferruginous gravels are actually anomalous in gold and copper along this boundary. It's not very far, but the idea here, if you have something here, it is still residual in the saprolite, and when you erode, you might be erode along this way. But if it's at some depths, and once you fill that sort of sediments and reach to that surface, it can be picked up along the next surface. So that's the most important idea of the mechanical dispersion. And actually, we have very good example from Eucla Basin where we find fresh sulfides actually coming along that sort of upper boundary between Cretaceous cover and the Eocene cover. So with this material, we saw that there's probably some sort of value high somewhere that reach to a level of mineralization to bring the fresh sulfide along this boundary. So that the main, and it's not actually above or below, it's just along that sort of boundary. So it could be very good potential method in area of very deep cover, not only the area of very shallow cover. This is an example where we see, as I mentioned to you, another way if you got a ship trail like a RC or AC drilling, and you got to this boundary and you have clays over clays, so kaolitic saprolite and, for example, paleochannel clays, hyperspectral analysis using the kaolin crystallinity and the abundance showing as you go up in this scale, you increase the kaolin crystallinity, so that in the saprolite, like residual saprolite clays, is mainly well crystalline, but the transported cover clay is mainly poorly crystalline. That's an example, but this situation is not a rule everywhere. For example, if you have the Permian cover and is weathered after deposition, it can give you also well crystalline kaolinite. But in the paleochannel situation, this is almost common. Another example here to mention to you, some of the boundary, when we try to understand or determine this boundary, some of the ratio, for example, titanium over zirconium ratio is very good to pick up the boundary between the Permian cover and the underlying fresh rock, very clear. In many drill holes, we have seen this evidence. But if we go for another cover and try to apply the same methods here, something in this cover, it doesn't work that well. And so we tried another ratio from the rubidium over zirconium in all of the holes pick up very well and boundary, that sort of unconformity between the cover and the underlying saprolite. Your beam anomaly is very good, especially if you have a Permian cover of felsic source rock over mafic rocks. Your beam anomaly doesn't change +1. Once it comes to the Permian cover, is less than 1, indicating felsic source rocks. Back again, when we have the bezoris on the surface of the gravel, back again. So this material is coming from the weathering of this material. So the landscape could be somewhere like this. So when you root this material from somewhere here along that unconformity, so this is coming from the same rock. So it might be you having some sort of paleo landscape like that. So that's a way of thinking about how you can determine these interfaces. Okay, and that's a very good example to show you the image that I showed you before, how the cover is reacted with groundwater. A lot of brecciation of the mudstone, sandstone interlayer cavities, and even brecciation of the uppermost part of the cover, and topped by this ferruginous gravel at the surface. So this material is also very good for sampling as well, and the uppermost part of that sort of cover. Of course, as I mentioned to you before, one important thing that also we sample for the interface, say that the cover itself is actually overlaying a residual weathering profile. And this residual weathering profile is actually complete residual weathering profile where you have an extensive layer of lateritic residuum is under this transported cover. So lateritic residuum actually is a very good sampling media in residual terrain because it can give you broader sampling spacing. Because you
Sorry, Walid, you might need to restart. I've just got to let some people in.
Okay. Do I need to admit them again?
Yeah, I'm getting them in again. Can you share your screen again?
Okay. Wow. Okay, okay, 1 second.
Sorry about that.
No worries. I will just try to see how can I do. I just need to close.
Are you able to share it again? Sorry about that.
Okay. No, I just close that one first. Okay. Yeah. Yeah. Can you please do again?
The host again? Yeah, cool. Yeah.
No, just can please do let me share it.
Sorry?
I can't share it. Sharing is not turned on.
Yeah, that's right. I'll make you host. Sorry, there you go. All right, go for it.
Yeah.
There you go. Should be good.
Yeah. Do you see the screen again?
Yes, sorry about that.
Okay, perfect. Okay, just to do. Yeah. Okay. So from here again, as I said to you before, the area of transported cover can also overlying the residual weathering terrain, and this residual weathering terrain have can be ended by thick layer and extensive layer of lateritic residuum. And having lateritic residuum in this area, you can also reach to that sort of the surface under the transported cover, along with unconformity and sampling this buried lateritic residuum, because it gives it has that advantage of wide spacing. You can even using sampling every 1 to 3 kilometers using this material. So that's one of the good advantage of even using the interface sampling, because you don't know if the transported cover is actually on residual terrain or covering residual weathering profile or even truncated weathering profile. If you over residual weathering profile, you have the advantage of very wide sampling in this situation. If you are in a truncated regime and the transport cover sitting on saprolite-hosted mineralization, then your spacing need to be like narrow, because the dispersion in the saprolite is narrower compared to the dispersion in the laterite. So this is also another way of looking for. So again, this is another example of where we expected to find this type of anomalies in this dashed line. In many of them, for example, in area of lateritic residuum, of course, at the surface, but sometimes this material is eroded and come above the unconformity, forming a thick, extensive ferricrete deposit. Some of them actually is being mined, for example, in Muller Well and Mount Gibson. This material is making the actual gold mine there have a high gold grade itself, even compared to the primary source, which was not there or even sub-economic. At the base of the palette channel, you can also have some sort of secondary mechanical dispersion of the gold itself when you sample this unconformity. Plenty of placer gold deposit can be found along that sort of unconformity. In area of Salt Lake, we have done one project, and also we have found a very good anomaly near the boundary with along the unconformity in Lake Rebecca, which is eastern to Kalgoorlie. A lot of anomaly is coming out of this interface samples here. Even within 10 meters of cover, you can pick up the anomaly very well. The only thing, and also when we go to the area of the Permian cover, the anomaly is mainly at the base of the cover here, mechanical dispersion, no chemical dispersion in the top of the cover, especially along Lansfield and Agnew. Here, that's also a very good example of this area of the Permian cover. And that's an example of where we sample the unconformity, especially in the area of the palette channel. There's two examples there in Ductingron stone belts, one in Garden Well gold deposit and the other one in Muller Well gold deposits. The difference between both of them is a setting within the palette channel. This is across the edge of the palette channel at Muller Well. Just the edge of the palette channel, there's extensive ferricrete deposit there, having a good grade. And when you compare that sort of grade in the ferricrete, you see it's much higher than those types of the sabrotic-hosted gold deposits. Both of them is economic, but that one is much shallower and extensive. It's extended along the main axis of the shoulders of the palette channel for more than 3 kilometers, and the width of it is 1 kilometer there. But when you go to the main gut of the palette channel, like the basal axis of the palette channels, you can see also another mechanical and also chemical dispersion. This is a mix of both of them. A lot of ferruginous gravel coming from the weathering of this material is just recycled within the palette channels and doesn't move very far from that area, and giving a very good anomaly that could also disperse away from the main mineralization. The mineralization is shear. Is hosted at the boundary between clay and ultramafic rocks, and is concealed by this tertiary palette channel that's almost 35 meters thick and 600 meters wide. Hypogene is mineralization extensive for 400 meters width, and gold dispersed at the base of the palette channels. Dispersion yellow is extended 0.1 and 0.5 kilometer, and compared to the 450 meter of this width of the main mineralization. And when you look for this material at the base of the palette channel over Garden Well, this is the main sample that has been sampled, which looks like is a ferruginous level driven from the underlying mineralization. And laser ablation ICP-MS samples, you can see it still contain gold and copper and arsenic. And when you see the sampling in this palette channel, this is the main mineralization. Sampling this material over the mineralization and away from the mineralization, both sides. You can see, for example, here only on this two maps, example of gold and copper, but there's also a lot of element also showing an anomaly. But just here, I'm showing gold and copper, and you can see it here is also anomalies in this material, which is actually sampling this material above the unconformity. This is very important on that sort of material. And the palette channel clay that we saw before along the Muller Well here, you can see this is the ferricrete deposit at the edge of the palette channel, and this is sabrotic gold underneath. You can see even the comparison between the extension and the source, so like the anomaly extension and the concentration there. And this is actually in the upper 6 meters from the surface. All of this material of the ferricrete either of yellow color or red color, is very, very good and showing this type of good high grade of gold. And this is the material that is being mined. Of course, it's very tricky because this material that is host gold is overlain by up to 2 meters of soil. It's completely barren. So it's very important when you do some soil sampling in the northern Yellowground. If it doesn't work, it doesn't mean that there's nothing there. It just means that soil is not working. But it could also hosting or just covering mineralized rocks or even mineralized regolith. When this has been tried to sample the termite mound around this area, when this material is up to 5 meters, you can see the termite mound over the mineralization in area of shallow cover less than 5, but above 5, you can see the difference. You can pick this mineralization when the cover is less than 5, it's above 5, termite mound doesn't work. And this is the gold analyzed by aquaregia, also doesn't show the mineralization from the surface. Just this profile is overlaying this material. So this is very extensive deposit. It's not picked up by soil or even termite mound if it's above 5 meters. Another good example of the hydromorphic dispersion here is actually at the edge of the hillgum. The work that we have done with gold resources, one of the best case studies that I like there, because this area is covered by sandy dunes, as you see here, and in between these sandy dunes are very extensive sand plains. It's mainly aeolian sand plains covering a vast area around this the deposit. Of course, this Yamana terrain here is existing along the boundary between the Yamana terrain and Portable terrain, and Gold Road is exploring the Drusi Hill and Yamana and Greenstone Belt here. And of course, you may know that the Groye gold deposit has been discovered by Gold Resources recently in 2013. It's sitting in the same area along that sort of the boundary. It's also covered by extensive sand plain. But under this sand plain, it is a thick cover that was actually interpreted by the Geological Survey of Western Australia to be a Permian cover. But actually, we didn't convince you with that when we see that sort of cover, because this cover is sitting on a saprolite and is not quite similar to the one that we saw at Agnew and Lancefield, which is a big boulder fresh at the base. So we take it at that time for granted as a Permian cover based on the mapping by the Geological Survey. But recently, when Gold Road started to drill a little bit toward more Eucla Basin, we started to see the Permian cover under this cover. So we give it a little bit much younger age, which we believe could be Eocene Hambleton sandstones or could be some Cretaceous. We don't know yet. So this cover now we're dealing with is younger than the Permian cover. So this cover is underlain by extensive layers of ferruginous gravels or duricrust or ferricrete before it's capped by the Aeolian sand. As you go toward the Eucla Basin, the cover is changing mainly into Cretaceous cover, mainly Madura shale, lower Cretaceous, overlain by Lungana sandstone of upper Cretaceous, and overlain by the Eocene Eucla limestones. Of course, we show you the location of the indicator mineral in this situation. I'm going to go and show you the details of the indicator mineral later on, but we target all these unconformities between the cover and saprolite, or even within the cover itself, or chemical interface, or very close to the surface here. Of course, when we sampling here in one of the recent projects that we have done with BHP, we found very exciting information about this boundary that may show that with a basement valley topography that brings some sort of fresh sulfides along this boundary. Is very good for targeting this type of indicator minerals. To show a good example of this type of interface sampling and how you use this interface, this is a Groye gold deposit, as I mentioned to you before. This is like a cartoon of 3D looking. Groye gold deposit, as you see, this is surface expression, is very narrow in the surface. The surface expression is very narrow. It's ranging up. The maximum width on the surface is almost 190, if I remember very well. And is overlain in the southern part of it is just a very thin cover there, mainly Aeolian sand, or could be 1 meter of, up to 1 meter of quaternary hard banais, colluvium and alluvium, before it's underlain by the upper part of the paleochannel sequence, red sandy clay and mottled clays there, and sitting on a saprolite. When we have this, the cover sitting on a truncated regime. This is not residual terrain. They mean if you have a saprolitic gold in this situation, make sure you expect that the dispersion will not be very, very thick across this top of the boundary. So meaning that you might need to narrow your spacing in this situation. And that's actually what's happening. This is the surface expression of the interface samples. There is not extensive. And we have done 3 profiles of logging and analyzing this type of the interface between the cover and the underlying saprolite. One of them is showing that sort of I'm not sure what's that. One of them is showing that sort of variation. So when you're crossing the boundary between this type of volcaniclastic, the intermediate mafic volcaniclastic to the main granite intrusion hosting the main mineralization, you can see very good anomaly of the gold and arsenic only over the mineralization and doesn't move to the other boundary. So that means that if this is like a maximum thickness is, or the maximum width is 190, so you need to reduce your spacing maybe to 100 meters or even less to get that sort of extension. But we focus mainly on the chemical interface as well, and what we look for here, that's boundary. Before we go to that, in the southern part of the Marmara terrain, especially in this part, we have also focused some sort of research there with one of the students with us, and done a lot of mapping in this area, and done a number of east-to-west sections just to see that the geometry of the cover, and that's what we got. Example of one of these sequences showing that the cover, it's the threshold is whether to saprolite and in some places eroded and overlain by this Permian cover, as we believe at that time, and covered by ferruginous gravel or loose or cemented, and then by aeolian sand. Some area have an area like this, residual terrain, almost residual terrain or semi-residual terrain, could be residual or could be transported this material. So, and this, what we look for those type of the surface ferruginous material, and we found actually different types. In the aeolian sand, we have seen this very nice and unique bezolis formed within the aeolian sand, mostly rounded or elliptical bezolis of different size. It's mainly sand grain cemented by iron and clays. That's within the aeolian sand. And the top, if we go to this area of the residual area, we can see either something looks as residual, like this duricrust, lithic residuum, or could be eroded and re-cemented again, forming this type of the ferric sheet. It can be also loose in some places. The top of the Permian cover as well was also ferruginous. I show you one of these examples. It can be forming this type of the bezolis as well at the very top most part of the Permian cover. Can be residual, can be transported, and can be also loose. So that's what we see in there. So we have focused sampling on all of this type of material to see if there's some variation or not. And this was a very good example to show how hydromorphic dispersion has been moved from this lateritic gravels or residuum or ferricite up through that aeolian sand. So we got sample from the lateritic residuum here. We got sample from this orthogenic bezolis in aeolian sand. We got sample from the matrix itself. We separate the matrix from the bezolis. So we get sample number 1, which is this blue bar. Sample number 2 is the orthogenic bezolis, this red bar. And the matrix around is this green bar. And one from the top is this orange bar. What we see here, gold is actually 2 times enriched in this aeolian, in this orthogenic bezolis in aeolian sand. The matrix around this is less, and as you go up is less. And this bezolis actually is in this image is in this location and very close to the unconformity, but in other it could be spread out and even could be in the soils. So we target to see this type of the bezolis. I'm going to show you how we did this later on. But the gravel underneath actually have this immobile element associated with the iron. So arsenic, bismuth, indium, lead, silver, and tin is mainly higher in concentration with the ferruginous gravel, probably with more iron enrichment in this ferruginous gravel compared to the orthogenic bezolis. But at least the main message here that the gold can move and even enrich more in this material compared to that material. There's a vertical dispersion happening here, and most likely there's also microbial process involved in precipitation of gold and other metal in this material. So we target this material. Gold was very excited and actually very helpful for us. And we target this material. This is one of the prospect gold and smoke push. We have going to the mineralization and get samples. With samples looking for the bulk soils, which looks like bulk soil. We have separated less than 75 and more than 2,000 micron with gravels. And from all of these samples, we collected 70 samples from the area, And actually, when we try to see these gravels, not all sample from the surface soil showing these gravels. So half of the samples actually we didn't get bezolis, so we asked Gold to provide auger or this AC duricrust, and we drill the rest of them getting this bezolis between almost 1 and 3 meters deep. And we've done the job, and the gold is much more enriched in the bezolis compared to the less than 75 fraction. And after we finished the project, we also tested the ultrafine soils, and actually the concentration is actually coming in between these two sizes. So actually the bezolis is showing even higher concentration than the ultrafine soil there, which gives the advantage of easy separation in the field and sieving rather than going to the ultrafine. But in general, all the site fraction are giving the response in your surface. This is the one sec, let's see that one. This is also a similar way of showing the gold here. The gold is also shown on one of the cross sections, showing a very good response over the mineralization. But actually, unfortunately, behind this map, we have a map of the arsenic, which is actually showing the same response as gold, higher in the bezolis, anomalous over the mineralization, the same pattern. The bezolis is higher concentration, followed by the ultrafine, followed by less than 75 in the soil fraction. So all of them is picking up. But the most important thing, there is no other anomaly except gold and arsenic in this situation. Sorry, this is the one that I'm showing about the arsenic. Similar anomalies in both fractions, but it's even higher in the bezolis compared to the less than 75. For that reason, the soil is anomalous. We try to see the vegetation in this situation. Remember, this is also sitting over the cover, ranging from maybe nothing until almost 45 meters of cover. This is when we sample the soil and found it's anomalous, and the bezolis is anomalous. We try to see the partial extraction and the vegetation to cross-section over the mineralization, showing very nice arsenic anomaly over the mineralization in the two profiles, which give indication, okay, why arsenic is only going to the vegetation. So we done the partial extraction analysis, 6 methods using potassium cyanide and iodides, hydrogen hydrochloride, concentrated, dilute, and 0.1 molar and 0.25 molar for extracting iron oxides and manganese oxides, and the potassium iodide and cyanide for extracting soluble gold, in particular gold. Sodium tetrapyrophosphate is extracting beta associated with organic matter, and water is to distilled water is to extract water soluble. What we saw, gold is mainly enriched or extracted by potassium cyanide and iodide, and partly by tetrasodium pyrophosphate, meaning that the gold moving as a particulate and soluble, and part of it in the soil mainly associated with organic material. But arsenic is actually mainly associated with organic material when extracted by sodium tetrapyrophosphate, and that's why maybe the arsenic can be controlled by biological process near surface and may be concentrated mainly by the vegetation near surface. At this stage, we're going to excited and we're going to tell Gold Road that this is a good method of picking the mineralization near surface without even drilling. Vegetation can pick up or going to the mineralization or area of anomalous area within the cover to pick up the mineralization. But wait until to see the surprise in the next few slides. When you see the mineralization, why we do see only gold and arsenic in anomaly only in the cover? The mineralization itself, this is a CT scan of one of the good core showing coarse green gold, pyrite, pyrrhotite, arsenopyrite. Concentration of gold is mainly showing gold and arsenic and sulfur. The rest of the other two groups here, each of them is less than 5. The other one is less than 50. So it's not anomalous in general, not higher concentration compared to these metals. And also TEMA maps of the mineralization showing arsenopyrite, pyrite, and pyrrhotite are the main dominant minerals there. So that arsenic and gold are the main dominant mineral, and those ones also disperse it to the cover to show the anomaly near surface. But when we go to the Tobin Hill, one of the other prospects there, we see that the gold is also moving across the whole cover and showing dispersion. So the cover near the surface, and you can see the anomaly in this type of the cover. The lower part is gravelly sandy, and the upper part is mottled and mainly concentrated with iron oxide there, and topped by these ferruginous gravels and aeolian sand. We have done the same process of looking for this type of material across the mineralization, and you can see that we see very good dispersion through the cover. This is a good mechanical dispersion. But again, with this type of barrier landscape here, that sort of drill hole showing also very good higher concentration there, but we don't know exactly what's happening. But there's also mechanical dispersion could be happening across this, whether this is coming from that source or could be something also in a different way, not sure, but it could be something here. But also when you have something like this, look for the barrier landscape of the unconformity of that sort of interface. Why we get excited in the beginning when we look for the mineralization, for the vegetation sampling. When we move to that prospect, we have seen the same response in Bizolis and in less than 75, very good gold anomaly, but actually there is no arsenic anomaly. And we were surprised why this is. We went to Tobin Hill, we looked for the mineralization. When we look, gold is also high, but arsenic is very low. This is a very low in ppm compared to the smoke push, which is a higher concentration, because there is no arsenopyrite in the system, and that's why we didn't see the arsenic anomaly near surface. We just only see gold. So it's a very good sampling media that reflects actually the underlying mineralization very well. And when we look for the surface material during laser ablation ICP-MS mapping, we have actually found that this orthogenic Bizolis in aeolian sand and this ferruginous gravel near the surface, both of them have a gold, visible gold, not a visible gold, but at least we map them using the laser ablation. You can see here the negative effect of the gold, clusters of gold, even dispersed through this material, or even within this orthogenic Bizolis, we can see some sort of cavity filling gold. It's minor veinlets of gold and this arsenic enrichment in this Bizolis. Now, when we go to look for the indicator minerals along this unconformity, the idea of sampling the indicator minerals, we normally look for the basal part of the transported cover, ideally when the cover is sitting over the fresh rock. We separate this type of the lowermost emitter, again, rather than sampling the main chemistry. We just separate the heavy minerals using the heavy liquids. It depends on what sort of heavy mineral you're looking for. We use the heavy liquid to get all the heavy minerals. And normally what we do is focusing on the range between 45 micron up to 1 millimeter, which is mainly the silt and sand size for them. Okay, so once we sample this at the basal part of the unconformity or along any other unconformity within this type of the material, we take them and do polish rounds and analyze them using TIMA or one of the SEM, and started to do quantification and looking for the mineral chemistry of these mineral grains, and started to understand what sort of ore deposit we can find. We have tested this in an area of shallow cover near Agnew and Lansfield, and we found fresh sulfide there over the mineralization. And we tried to see in this situation, actually, we found a very good and promising area, an area which completely greenfield exploration. No mineral deposit has been discovered yet, because we have covered up to 800 meters in the maximum area. We can see it's vary from 400 to 800 meters. But of course, it is impractical to sample all of that. So we focus mainly on using these indicator minerals, and we found very good promising results. I'm not going to show it today for this area, but sooner will become available for public. Just to go for the indicator minerals to show you what sort of indicator mineral we're looking for. I have divided the indicator minerals here actually into 4 types. The one which is called the trital indicator mineral, coming by mechanical weathering to come at the basal part of the along the unconformity, and this is trital by mechanical weathering. The second type is a super G. You can put the groundwater table within the cover and do oxidation of this mineral, so you can chalcopyrite can move to chalcocite or even covellite or secondary super G mineral, but after the trital grades. We have other residual or inherited indicator mineral, the mineral that doesn't react during weathering. Some of them, gold, for example, cannot be reacting during weathering unless if there's some sort of ligand or complex that can move them later on. But generally, if there's no apparent legend, it can be residual in there. Or be residual like some sort of supergene sulfides. It can be also diagenetic in some of the paleo-channel clays. This is an example of this the trital grain. Some of them can also have some sulfide inclusions, and gold also can be residual. Some of that the trital sulfide, as you see it here. Example of the Permian cover in Lansfield. That's a Permian diamectite. Lower part is fresh, as you see it here. The upper part is weathered, as you see it here. Fresh fragment of different polymetric sediments cemented by iron oxide cement. There is not intensive weathering. We sampled the basal part of that sort of unconformity, which you can see it's really highly ragged here. So it could be had some sort of traps in between. So the mineralization in the higher part, and you erode them, you maybe bring it in the lower part. So you don't expect it to find distal footprint rather than proximal footprint. So example here, we look for the mineralization in a heavy mineral concentrate. We mineral concentrate of the mineralization. That's example from the gold deposits and the chemistry. So the chemistry here showing the gold deposit there is gold, arsenic, cobalt, zinc, cadmium. All of these metals is initiated in the mineralization. Mineralogically, it's showing that the gold is associated with pyrite and other metals like cobalt, gerstolfite, cobalt-type gerstolfite, chalcopyrite, bentlandite, galena, arsenopyrite, gold, scheelite, and sphalerite. And all of these minerals actually is sulfide minerals showing you the same element. So the mineralogy is matching with the chemistry. But when we sample the base of the cover in a number of drill holes, and that mainly over the shear zone here and even to the eastern part of the shear zone, knowing that the direction of the glacial outflow during the Permian formation is towards southeast, we found this is an example of one of the sample at the base of the cover, so plenty of fresh sulfide there. And this is an example of some of these grains. You can see fresh sulfides like pyrite. You can see also some of the chalcopyrites, some secondary super G minerals as well here. Some of the gold as well, still fresh in that area. So we sample the basal part on all the drill holes, and we do some quantification of these minerals. And we started to see enrichment of some of them actually over the mineralization and moving toward the direction of the ice flow. The main disadvantage of this area that we don't have that many drill holes around this area. So we don't know exactly if there's some sort of dispersion here or not, or something happening here or not. We mainly see it here. And the maximum dispersion based on the available drill hole is almost 500 meters in the direction of the flow. As I mentioned to you, the advantage of this area that if you have mineralization here in the direction of flow, you might be putting there very close to the source. And when we sample the interface here, and even and also the heavy minerals, we found the interface sampling is also showing concentration of these metals, gold, arsenic, zinc, cadmium, cobalt, and zinc over the main mineralization. And that's what we ending up. This is a very good sampling media of sampling this using the interface and also the indicator mineral, because it will pick up some of the heavy minerals at the base of the cover. And even once you go these traps, you're going to see that the main idea that people thinking that this Permian cover is forming a paleo channel, which is actually not. It's actually isolated pockets in the ancient landscapes. So once you go away from the land, from these pockets, you're going to go for a residual weathering profile over basement straight away. So it's not a continuous there. It's mainly actually is a detrital material. And I will leave it for you because I also almost 1 hour and 5 minutes. Sorry for that sort of time. I will leave it there. And yeah, I'm happy to receive any questions.
Amazing. Thank you so much, Walid. That was a fantastic walkthrough of the work you've been doing across the Yilgarn in Western Australia. So, and obviously it's really built up a great story as well about the interaction between the cover and the basement with those interfaces. Thank you. We've got loads of questions in the chat. So I think they might have left now. Steve Hill had a couple of questions. If you're happy to answer them still.
Yeah.
He was wondering, he said how Waldo relates silicification to a process associated with arid climates. He understands it's in the youngest cover, but what processes in arid climates are encouraging this silicification, do you think?
The silicification, yeah, the silicification is mainly happening with arid climate, because the released silica in general can be precipitated during the arid climate, especially when the high rate of evaporation. You can drop all of these type of silica and calcium carbonates and calcium sulfates. So mainly by increasing the evaporation rate on the silica, you can drop all of this silica with arid climate. You are muted.
Do we have any in the audience? like who've been wanting to give a question? Otherwise, I'll keep going through the chat. Feel free to come off mute and put your video on. Cool. All right. So I've got another one from the chat. What are the constraints on grain size and sample size when sampling transported cover interfaces such as Permian dimictite?
What sort of grains? Sorry, can you repeat it again?
Oh yeah, sorry, back to that. What are the constraints on grain size and sample size when sampling transported cover interfaces such as the Permian dimictite? Because obviously it can be quite a mix.
Yeah, look, what we have done in general here, we try to get the size of the sand and the silt, avoid less than 45 because it could be moving a little bit far distance. So we don't want it to go very far. Like try to find something close by. And big boulders, it will give you a lot of it can also give you information, but big boulders, we try to avoid those ones because the minerals can be concentrated in the sand and silt size. You can look for them in the gravels, but normally we avoid the bigger size fraction, the gravel size, and less than the clay size.
Fantastic, thank you.
Just on top of that, mainly you can also do some sort of size fraction. You can test all of them. There's no problem. Canadian, for example, is doing using different size fraction, like as we use here in terms of the soils. But in general, you're not looking also for the ultra fine fraction, the very coarse fraction. They archive them if they want to come back, but the main size fraction could be up to 2 millimeter if you wish. Between 45 and 2 millimeter is the ideal size fraction.
That's great, thank you. We had a question from Clay. Where the Permian is not oxidized, the rubidium zirconium will reflect the Archean protolith. I can't see what this is. Oh, I've got things in the way. Is good for Eocene and younger Yamana. So that's an observation from Clay. So thanks for that.
That's right. Yeah, just a clarification.
Yeah. Is it a clarification or a question? I didn't.
Oh, sorry.
I don't know, because I think in your image you had the zirconium-rubidium ratio of the Permian marking quite an unconformity, but I guess when we used to use it originally, it was to differentiate the Eocene and younger, and the Permian material, because it was largely unweathered and still just sort of silts and dimictites, it reflected the Archean rubidium zircon ratio. So it didn't work as well for us there in that material, but certainly the younger, more oxidized and transported material, it did.
Yeah, this type of ratio can vary from one cover to the other cover. So if you have something like this, we can say now you see in cover over felsic, so it can work. If you go maybe over, if you find the Permian cover, you might see some changes happening when you hit the Permian cover. So I'm not saying that this is something that you can use everywhere, but at least you can try to find some sort of ratio to determine that sort of cover interfaces. Not necessarily to be over that volume. Yeah,
it did work extremely well at Yamana. Primarily because the rubidium was just stripped out of the transported material.
Yeah,
was what really worked there.
Yeah. By the way, we have used the same ratio for the same cover there on Battles formation, and the rubidium over zirconium also worked very well.
Excellent.
Yeah.
Thanks, Clay. Okay, so this is from Mark Rundle. What is the evidence that the phytoliths are orthogenic in the aeolian sand and the Permian?
Yeah, that's a very good question. Actually, the matrix and in the visuals and the matrix around the same. There's nothing around in it. There's nothing strange. When we see, for example, the top of the Permian cover there, what we call the Permian at that time, and we see some sort of similar visuals in the aeolian in the Permian cover. And what we see that the visual there was almost hematite and goethite rich, no quartz grains. And when you see the matrix itself, you see quartz and feldspar and mica. So when you see some sort of variation between the matrix and the inner structure of the visuals itself, you can indicate if it's orthogenic or residual. So some sort of matrix variation, mineralogical condition of the matrix.
That's great. I'm sorry, I did note too. I'm looking at a little screen here.
And also, there's no much cortex. It looks like it's mainly nodules. It's like a massive structure there, and the boundary with the boundary in outgrowth, the boundary with the matrix is not very sharp. It's not very sharp in a way.
Great, thank you.
Yes.
All right. There's a few comments in here. I don't know whether Leah, you'd like to pick up on some of the questions and comments that you've had in the notes. So I think there's a bit of talk about the Cenozoic fill within the paleochannels varies. Below the Menzies line, middle, late Eocene, younger, and above it, there's not been any palynology and dating done. So I think there's a bit of a chat about sort of you know, some of those assumptions in some of the slides, whether there might be some further work that could be done to sort of differentiate on those ages and fine tune it as part of this work or future work.
Yeah. I'm just telling you something important that when we look for this type of age, it's not easy because most of this type of cover is not mineralized except those organic rich clay, and we find actually three types of organic rich clays just to see how complex it is. When we look for Eucla basin, we see Maduro province. That's a Cretaceous. There is some palynology done there, and it's giving Cretaceous age. When we move, for example, to some of those Permian cover itself, there's also glacial lacustrine Permian organic rich or carbonaceous mudstone in the Permian as well. And there's also some example when we see that sort of palynology, we found Permian or Permian-Triassic age. And some recent palynology has been done on some of the paleochannels, the Miocene age. So it needs to be done systematically. Definitely you will find different ages when you do the palynology of this type of organic rich clay everywhere. The sand and the stuff that is not fossiliferous, unless if you go to the southern coast of Western Australia, where you see the Eocene cover a lot of fossil, marine fossil there, like a sponge and all of that stuff. You can see some sort of age. You can date that one, but the majority of the cover is actually, as you know, is not fossiliferous or doesn't have something to map at the moment. You're muted. We're both muted.
It does. It has loads of fossils in it.
Yeah.
There's loads. I've done sequential palynology through these whole paleo channels from the base of them all the way up. There's plenty of fossils in them. And as far as I know, the only actual palynology done on any of that Permian stuff was Black House in 1978.
Yeah.
And everyone seemed to have grabbed hold of this and said, oh yes, everything that looks remotely glacial must be Permian because of John Blackhouse's work. But he went back to his own work a couple of years later and said, oh no, it's all undifferentiated Mesozoic. So we're all suggesting that this is Permian cover, but no one actually knows because no one's dated it. That there's no direct dating evidence. It's just indirect.
Yeah, that's exactly right. I mean, those type of sediment is, you can see it and you think it's different, specific age, but when you do the palynology, it's another age. So it needs to be done. I mean, if there would be, of course, some science to be done on the dating of this type of clays, just to see what is the actual age of those ones. But we have a variety of this material anyway.
Awesome, thanks. Are there any other questions across the audience? I can see there's a lot of passion for this area, so it's been really great to have you here today, William.
No worries.
Going through this, I mean, obviously, lots of potential too. It's really exciting to see all the work that's been done, and you know, the type of projects that are happening too. And it's obviously really rich in geology and commodities. So thank you. Yeah, we also do at the moment with a focus mainly on the indicator minerals, especially for developing some sort of like a workflow for the indicator minerals, which is very important. Especially we have a plenty of stuff. For example, the work that we have done in the Eucla basin, it can have a potential somewhere to the other end of the South Australian part, of course. When we look for those samples, it could be very, very beneficial of looking for the interface sample, especially when you have a very thick cover like this, and you don't want it to look for the chemistry or doing a lot of analysis. It can be just summarized around the unconformity, looking for heavy mineral content to see if there's something or not, because
the work that we have done there is indicating there could be some potential in the area based on that, just looking for some of the analyzing that some of these sulfides and using some sort of variation diagrams to indicate the ability of the mineralization within the area. Yeah, that's one of our main focus at the moment here in the Rivers area.
Yeah, there's been a bit of work done previously within DCRC with Helene Bordet around Prominent Hill as well. So yeah, it's definitely really helpful in those areas of cover.
Yeah, definitely.
Great.
Yeah, perfect.
All right. I reckon we're done, Walid. We could talk all day, I can imagine.
Perfect.
But thank you so much for taking your time today to come and talk here on for our ARGA webinar. It's been really great to hear from you.
Yep. Thank you, Wally. Thank you, Anna. Thanks to everybody.
Thanks, Nadia.
Yeah, it's a really great chance to connect across it. So I guess in other ARGA news, we've got a MESA joint webinar in November with Dr. Gresley Wakelingham. So really looking forward to that. And that'd be really fun. And in the new year in February, we've already lined up our next talk. Was it allanite, Leah? Am I getting that right? Yes. So it's going to be really interesting with Roland Gotthard. So make sure you check out our LinkedIn. We've got all the links there to sign up. And obviously you found us here today with Walid. So thank you again, Walid, so much. It's been wonderful to have you here.
Thanks. Thanks, everyone. Thanks.
I hope everyone has a great day and we'll see you soon.
See you. Bye.
Thank you. Thanks, everyone.
Thanks, everyone. Bye.
Thanks, Walid.
Thanks. Bye.
Have a great day.
And you too. Bye.